Tonight, we're going to witness the most violent event in the modern universe. Not a supernova. Something far worse. Imagine a star so massive that when it dies, the explosion releases more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. An explosion so powerful, it doesn't just destroy the star. It warps the fabric of space-time itself, fires jets of matter at 99.9% the speed of light, and for a brief moment outshines every single star in its entire host galaxy combined. This is a hypernova, and what actually happens during one, the real physics of it, is so extreme that it pushes everything we know about matter, gravity, and energy to the absolute breaking point. By the end of tonight, you'll understand exactly why. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. To understand what a hypernova is, you first need to understand the kind of star that can produce one. Because not every star dies in an explosion. Most stars don't. And even among the stars that do explode, most of them produce ordinary supernovae. A hypernova requires something rarer, something more extreme. It requires a monster. A star so massive, so luminous, so physically extreme that it burns through its nuclear fuel at a rate that would seem almost reckless compared to a star like our sun. And to appreciate just how extreme these stars are, we need to start with what we know. We need to start with ordinary stars and work our way up. Our sun is a fairly typical star. It's what astronomers call a G-type main sequence star, with a surface temperature of about 5,500 degrees Celsius. It's been burning steadily for about 4.5 billion years, and will continue for another 5 billion years or so before it begins to die. The sun generates its energy through nuclear fusion in its core. Hydrogen atoms are squeezed together under enormous pressure and temperature, fusing into helium. This process converts a tiny amount of mass into energy according to Einstein's famous equation, E equals mc squared. Every second, the sun converts about 600 million tons of hydrogen into helium. About 4 million tons of that mass is converted directly into energy every single second. That sounds like a lot, and it is. But the sun has an enormous amount of hydrogen to burn through. It's so large and has so much fuel that it can sustain this process for roughly 10 billion years total. That's the life expectancy of a star like the sun. 10 billion years of steady, stable hydrogen fusion. Now, here's something that might seem counterintuitive. More massive stars don't live longer than less massive ones. You might think that a star with 10 times the sun's mass would have 10 times as much fuel and therefore live 10 times as long. But it doesn't work that way. More massive stars burn their fuel much, much faster. The reason is gravity. A more massive star has stronger gravity pressing inward on its core. To prevent itself from collapsing under that gravity, the core has to generate more energy, which means burning fuel at a higher rate. The relationship is dramatic. A star with 10 times the sun's mass doesn't burn fuel 10 times faster. It burns fuel roughly 3,000 times faster. This means it lives not 10 times as long as the sun, but only a few hundredths as long. Instead of 10 billion years, a 10 solar mass star might live only about 20 to 30 million years. That sounds like a long time by human standards, but in cosmic terms, it's a blink. The sun has been burning for 4.5 billion years. A 10 solar mass star would be born and died 200 times over in that same period. And as stars get more massive, the trend gets more extreme. A star with 25 times the Sun's mass might live only about 7 million years. A star with 40 solar masses might last only about 4 to 5 million years. A star with 60 or 80 or 100 solar masses lives even shorter, perhaps only 2 to 3 million years. These are stars that burn through their fuel with extraordinary speed. They're the brightest, hottest, most luminous stars in the galaxy. They shine with a brilliance that can be millions of times greater than the Sun's luminosity. They're visible across enormous distances, and they die young, always young, every single one of them. The stars that produce hypernovae are at the extreme end of this spectrum. We're talking about stars with initial masses of roughly 40 solar masses and above. Some of them might start their lives with 60, 80, or even over 100 solar masses. These are genuinely rare objects. In the entire Milky Way galaxy, with its hundreds of billions of stars, there are probably only a few thousand stars this massive alive at any given time. They make up a tiny fraction of the total stellar population. Most stars in the galaxy are small red dwarfs, dim and cool and long-lived. Stars massive enough to produce hypernovae are the opposite. They're enormous, blazing, and short-lived. They're the cosmic equivalent of a candle that burns 1,000 times brighter than normal, but lasts only a fraction of the time. Let's talk about what these stars actually look like. A star with 40 or 50 solar masses is not just a bigger version of the Sun, it's a fundamentally different kind of object. Its surface temperature might be 30,000 to 50,000 degrees Celsius, compared to the Sun's 5,500. At these temperatures, the star glows with an intense blue-white light. It's not yellow like the Sun. It's not orange or red. It's blue. Searingly, blindingly blue. If you could somehow replace the Sun with one of these stars, the Earth would be vaporized almost instantly. Not just heated, vaporized. The radiation output would be so intense that the rocky surface of our planet would be stripped away in minutes. These massive blue stars are also physically large, though not as large as you might think. Red supergiant stars like Betelgeuse are much wider in diameter, but they're actually less massive. The most massive stars tend to be blue supergiants, or Wolf-Rayet stars, and while they're much larger than the Sun, they're not the widest stars in the galaxy. A typical blue supergiant might have a radius of about 20 to 30 times the Sun's radius. That's large, but Betelgeuse, which is only about 15 to 20 solar masses, has a radius of roughly 700 to 800 times the Sun's. The most massive stars are compact for their mass. They pack an extraordinary amount of material into a relatively small volume. And this density is part of what makes their deaths so violent. Now, many of the stars that ultimately produce hypernovae go through a dramatic transformation during their lives. They don't die as the blue supergiants they were born as. Instead, they evolve into something called a Wolf-Rayet star. This is a crucial part of the story, so let me explain what happens. A very massive star, one with perhaps 40 or more solar masses, generates such intense radiation from its core that the light itself pushes on the star's outer layers. This is called radiation pressure, and in these extreme stars, it's powerful enough to physically blow material off the surface of the star. The star is literally too luminous for its own good. Its own light is tearing it apart. Over millions of years, the star sheds its outer layers of hydrogen into space. Layer after layer is stripped away by these fierce stellar winds. The mass loss rates are staggering. Some Wolf-Rayet stars lose mass at a rate equivalent to one solar mass every 100,000 years or so. That might sound slow, but over a few million years, the star can lose half or more of its original mass. What's left behind after this stripping process is the hot, dense core of the star, now exposed to space. This is the Wolf-Rayet star. It's essentially a naked stellar core, a star that has been stripped of its outer hydrogen envelope. The surface of a Wolf-Rayet star isn't hydrogen, like the surface of the Sun. It's heavier elements: helium, carbon, nitrogen, oxygen, depending on how much stripping has occurred. The surface temperatures of Wolf-Rayet stars can exceed 100,000 degrees Celsius. They're among the hottest stars known. They're also incredibly luminous, often hundreds of thousands of times brighter than the Sun. Wolf-Rayet stars are rare. There are probably only about 1,000 of them in the entire Milky Way galaxy. They represent a brief phase in the life of a very massive star, lasting perhaps a few 100,000 years before the star reaches the end of its life. But this phase is critical for understanding hypernovae, because the stripping of the outer layers changes the dynamics of what happens when the star finally dies. Without that thick blanket of hydrogen surrounding the core, the jets that form during the death of the star can punch through the remaining material more easily. The stripped envelope makes the hypernova mechanism possible in ways that a star with its full hydrogen envelope intact might not allow. We'll come back to this later when we talk about how the explosion actually works. Now, let's talk about what's happening inside one of these stars during its life. Because the interior of a massive star is one of the most extraordinary environments in the universe, and understanding it is key to understanding why the death is so violent. In the core of a massive star, nuclear fusion proceeds through a series of stages. Each stage fuses heavier and heavier elements, and each stage is shorter than the last. The star begins by fusing hydrogen into helium in its core. For a star of about 40 solar masses, this hydrogen-burning phase lasts roughly 4 to 5 million years. It's the longest phase of the star's life, the main sequence phase, where the star sits on the main sequence of the Hertzsprung-Russell diagram, steadily converting hydrogen to helium. When the hydrogen in the core is exhausted, the core contracts and heats up. The temperature rises high enough for helium fusion to begin. Helium nuclei, which are the same as alpha particles, fuse together to form carbon and oxygen. This helium-burning phase is much shorter than the hydrogen-burning phase. For a 40 solar mass star, it might last about 500,000 years. Still a long time by human standards, but only about a tenth of the hydrogen-burning phase. When the helium is exhausted, the core contracts again. The temperature rises further, carbon fusion begins. Carbon nuclei fuse to produce neon, sodium, and magnesium. This phase is even shorter. For our 40 solar mass star, carbon burning might last about 1,000 years. We've gone from millions of years to hundreds of thousands of years to just 1,000 years. The acceleration is dramatic. After carbon comes neon burning. Neon nuclei are broken apart by high-energy photons and then reassembled into heavier elements like oxygen and magnesium. This phase lasts roughly a year. 1 year. The star spent millions of years burning hydrogen, and now it's burning through an entire fusion stage in a single year. Next comes oxygen burning. Oxygen nuclei fuse to produce silicon, sulfur, phosphorus, and other elements. This phase lasts about 6 months to a year. The core temperature at this point is roughly 2 billion degrees Celsius. The density is extraordinary, millions of times denser than water. Finally, the last stage, silicon burning. Silicon nuclei fuse to produce iron and elements near iron on the periodic table, things like nickel, cobalt, and chromium. This is the final fusion stage, and it's breathtakingly short. For a massive star, silicon burning lasts approximately 1 day. 1 single day. The star spent 4 or 5 million years burning hydrogen, and now it's burning through its final nuclear fuel in less than 24 hours. Some models suggest silicon burning in the most massive cores can be completed in just a matter of hours. At this point, the star has developed an internal structure that astronomers often compare to an onion. There are concentric shells of different elements, each representing a different fusion stage. The outermost layer, if it hasn't been stripped away, is hydrogen. Beneath that is a shell of helium, then carbon, then neon, then oxygen, then silicon. And at the very center, at the innermost core, sits a ball of iron and iron group elements. This iron core is the endpoint, the final product of stellar nucleosynthesis, and it represents a death sentence for the star. Here's why. Every fusion reaction up to this point has released energy. When hydrogen fused into helium, energy was released. When helium fused into carbon, energy was released. Every step of the way, fusion produced energy, and that energy created the outward pressure that supported the star against its own gravity. But iron is different. Iron sits at the peak of the nuclear binding energy curve. It has the most tightly bound nucleus of any element. Fusing iron into heavier elements doesn't release energy. It requires energy. It's an endothermic process. The star has been generating energy through fusion for millions of years, and now it's hit a wall. The iron core cannot fuse into anything heavier without consuming energy rather than producing it. This means the iron core is inert. It's just sitting there, growing larger as the silicon burning shell above it continues to dump more iron onto it. The core is supported not by fusion energy but by a quantum mechanical effect called electron degeneracy pressure. This is a consequence of the Pauli exclusion principle, which says that no two electrons can occupy the same quantum state. In the ultra-dense conditions of the iron core, electrons are packed so tightly that this quantum pressure is the only thing holding the core up against gravity. But there's a limit to how much mass electron degeneracy pressure can support. This limit is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subramanian Chandrasekhar, who calculated it in the 1930s. The limit is about 1.4 solar masses. As long as the iron core remains below this mass, electron degeneracy pressure can hold it up. But the silicon shell keeps burning, keeps adding iron to the core keeps growing, and eventually, inevitably, it crosses that threshold. In a star massive enough to produce a hypernova, the iron core grows large, very large. Depending on the star's initial mass, rotation, and metallicity, the iron core might reach 1.5, 1.8, or even over 2 solar masses before the critical moment arrives. This is larger than the iron cores in less massive supernova progenitors, and this difference in core mass is one of the key factors that determines whether a star produces a normal supernova or something far more extreme. When the iron core exceeds the Chandrasekhar limit, electron degeneracy pressure can no longer support it. What happens next occurs with terrifying speed. The core begins to collapse, not slowly, not gradually. The collapse happens in a fraction of a second. The iron core collapses at speeds that can reach 70,000 kilometers per second. That's nearly a quarter of the speed of light. In less than a second, the core that was the size of a planet compresses down to a sphere just a few dozen kilometers across. During this collapse, two things happen that accelerate the process and make it essentially unstoppable. First, the intense pressure forces electrons into protons, combining them through a process called electron capture or inverse beta decay. This produces neutrons and neutrinos. The electrons that were providing the degeneracy pressure are literally consumed, removing the very force that was holding the core up. Second, the extreme temperatures cause iron nuclei to break apart into individual protons and neutrons, a process called photodisintegration. This process absorbs enormous amounts of energy, robbing the core of thermal pressure. Both of these processes work together to accelerate the collapse. The core is falling inward, and every physical mechanism that could slow it down is being systematically destroyed. This is the moment everything changes. This is the threshold. For a less massive star, say one of 8 to 25 solar masses, the collapse will be halted when the core reaches nuclear density and neutron degeneracy pressure kicks in, forming a neutron star. The infalling material will bounce off the surface of that neutron star, generating a shock wave that, with the help of neutrinos, will blow the star apart in an ordinary core collapse supernova. But for the progenitors of hypernova, the stars we've been talking about tonight, the story takes a darker turn. The core is too massive. The collapse doesn't stop at a neutron star. It keeps going. The mass is simply too great for neutron degeneracy pressure to support. What forms instead is something far more extreme, far more exotic, and far more dangerous. The core collapses past the point of no return and forms a black hole. And that black hole, born in the heart of a dying giant, is about to power the most violent explosion the universe has ever known. But before we get to that explosion, you need to understand exactly what happens in those critical milliseconds when the core crosses the line from neutron star to black hole. Because the physics of that transition, the difference between a core that bounces and one that doesn't, is what separates a supernova from a hypernova. It's the difference between a firecracker and a bomb. And the details of how that black hole forms, how matter piles onto it, and how the rotation of the original star creates the conditions for something truly catastrophic, that's where the real story begins. Let me set the stage. The iron core has just collapsed. It's falling inward at a significant fraction of the speed of light. The outer layers of the star, the shells of silicon and oxygen and carbon, they don't know yet that the core has vanished beneath them. Information about the collapse travels outward at the speed of sound in the stellar interior, and the speed of sound, while fast, is far slower than the speed of light. There's a delay. The outer layers are still hanging there, suspended, unaware that the floor has just been pulled out from under them. For a brief moment, a fraction of a second, the star looks the same from the outside. An observer watching from a safe distance would see nothing unusual. The surface of the star would appear calm, unchanged, normal, but deep inside, the most catastrophic gravitational event since the Big Bang is underway. Trillions of tons of matter are being compressed into a space smaller than a city. Temperatures are soaring past hundreds of billions of degrees. Neutrinos are streaming outward in such numbers that they carry away more energy in 10 seconds than the sun will radiate in its entire lifetime. The density at the center is exceeding the density of an atomic nucleus, packing more mass into each cubic centimeter than exists in an entire mountain on Earth. And then the outer layers begin to fall. Not gently, not slowly. They plunge inward like an avalanche. Millions of solar masses worth of stellar material begins a freefall toward the newly formed singularity at the center. The star is collapsing from the inside out. The surface might still look normal, but inside, the star is imploding. What happens next depends critically on one thing, one single physical property of the original star that determines whether this collapse produces a whimper or a cataclysm. That property is rotation. How fast the star was spinning before it died. And for the progenitors of Hypernova, the answer is fast. Very, very fast. Because when a rapidly rotating core collapses, when all that angular momentum is compressed into a tiny space, something extraordinary happens. Something that turns the collapse itself into a weapon. That's what we're going to explore next. How a collapsing, spinning core creates the most powerful engine in the universe. An engine that can turn the death of a star into the birth of a black hole, a gamma ray burst, and the most energetic explosion the cosmos has ever produced. Let's pick up right where we left off. The iron core has just crossed the Chandrasekhar limit. Electron degeneracy pressure has failed, and the core is now in freefall, collapsing inward at tens of thousands of kilometers per second. This is the moment that separates a hypernova from everything else. This is where the physics diverges from what happens in an ordinary supernova. And to understand that divergence, you need to understand what happens in a normal core collapse supernova first, because only by seeing how a regular stellar death works can you appreciate just how different and how much more violent the hypernova mechanism truly is. In a normal core collapse supernova, the kind produced by stars between roughly 8 and about 25 solar masses, the iron core collapses until it reaches nuclear density. Nuclear density is the density of matter inside an atomic nucleus, about 230 million tons per cubic centimeter. At this density, the strong nuclear force, the force that holds protons and neutrons together inside atoms, kicks in and provides a new source of pressure. This is called neutron degeneracy pressure, combined with the repulsive component of the strong nuclear force at very short distances. The core suddenly stiffens, it becomes incompressible, it's like a ball of nuclear matter, incredibly dense but rigid. And the infalling material, all the stellar layers plunging inward at enormous speeds, slams into the suddenly rigid core and bounces. That bounce sends a shock wave outward through the star. Think of it like dropping a bowling ball onto a trampoline. The ball hits the surface gives way and then snaps back, launching the ball upward. Except in this case, the bowling ball is the inner layers of a massive star, and the trampoline is a newly formed neutron star. The shock wave propagates outward at thousands of kilometers per second, tearing through the overlying layers of silicon, oxygen, carbon, helium, and hydrogen. This is the supernova explosion. But there's a complication. The shock wave doesn't just cruise smoothly through the star. As it moves outward, it encounters infalling material still plunging inward. The shock has to push against this infalling matter, and that costs energy. The shock also loses energy to photodisintegration, breaking apart iron nuclei in the material it passes through. Within milliseconds of forming, the shock wave actually stalls. It stops moving outward. It just sits there, a standing shock wave with material piling up on both sides. If nothing else happened, the explosion would fail. The shock would dissipate. The star would collapse completely. No supernova, just a quiet implosion. What saves the explosion is neutrinos. During the core collapse, an enormous flood of neutrinos is produced. These are ghostly subatomic particles that barely interact with matter. Under normal circumstances, a neutrino can pass through a light year of solid lead without hitting anything. But the conditions behind the stalled shock are so extreme, so incredibly dense, that even neutrinos start to interact with the matter there. A small fraction of the neutrino energy, perhaps 5 to 10%, is absorbed by the material behind the shock. This energy deposition reheats the stalled shock, reviving it, pushing it outward again. This is called the neutrino-driven mechanism, and it's the leading model for how ordinary core collapse supernovae work. The revived shock blasts through the remaining stellar envelope, and the star explodes. What's left behind at the center is a neutron star, an incredibly dense object about 12 to 20 kilometers across, containing roughly 1.4 to 2 solar masses of matter compressed to nuclear density. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. The neutron star spins rapidly, often hundreds of times per second, and has an incredibly strong magnetic field. It's one of the most extreme objects in the universe, but it's stable. It sits there at the center of the expanding supernova remnant, slowly cooling, slowly spinning down, existing as a permanent monument to the star that died. This is how a normal supernova works. Core collapses to a neutron star, bounce, shockwave, neutrino reheating, explosion, neutron star left behind. The total energy released is about 10 to the power of 46 joules, with the vast majority of the energy carried away by neutrinos. Only about 1% of the total energy, roughly 10 to the power of 44 joules, goes into the kinetic energy of the explosion itself, the actual blasting apart of the star. And only a tiny fraction of that, about 10 to the power of 43 joules, is released as visible light. That's why supernovae are bright, but they're not the brightest things in the universe. Most of their energy is invisible, carried away by neutrinos that stream through the universe unseen. Now, here's where the hypernova diverges. In a hypernova progenitor, the iron core is more massive, significantly more massive. Instead of 1.4 solar masses, the core might be 2, or 2.5, or even 3 solar masses when it begins to collapse. This extra mass changes everything. The core still collapses, it still reaches nuclear density, neutron degeneracy pressure and the strong nuclear force still try to hold the collapse. There might even be a brief moment, lasting perhaps a milliseconds, where a proto-neutron star forms. A hot, bloated, newly born neutron star struggling to support itself against the weight pressing down on it. But the weight is too great. The mass is above the Tolman-Oppenheimer-Volkoff limit, which is the maximum mass a neutron star can have before gravity overwhelms neutron degeneracy pressure. This limit is somewhere between about 2 and 2.5 solar masses, depending on the equation of state of nuclear matter, which is something physicists are still working to determine precisely. When the proto-neutron star exceeds this limit, there's no bounce. Or rather, whatever bounce occurs is immediately overwhelmed. The core doesn't stabilize. It doesn't form a rigid ball of nuclear matter that can deflect the infalling material. Instead, the core keeps collapsing. Neutron degeneracy pressure fails just as electron degeneracy pressure failed moments earlier. There is no known force in physics that can halt the collapse now. But what's happening to the matter itself during these final milliseconds is extraordinary. As the proto-neutron star struggles and fails to stabilize, the material at its center is being subjected to conditions that don't exist anywhere else in the observable universe. At densities exceeding 2 to 3 times nuclear density, the matter enters exotic states that physicists still don't fully understand. Under normal conditions, neutrons and protons are distinct particles inside atomic nuclei. But at these extreme densities, the boundaries between individual neutrons begin to blur. The neutrons are packed so tightly that they start to overlap, and the quarks inside them, the fundamental building blocks that make up each neutron, begin to interact with quarks from neighboring neutrons. Some theoretical models suggest that at these densities, a phase transition occurs. The quarks, normally confined inside individual neutrons by the strong nuclear force, may become deconfined, breaking free of their parent neutrons and forming a new state of matter called a quark-gluon plasma. This is the same state of matter that existed in the first microseconds after the Big Bang, before the universe cooled enough for quarks to condense into protons and neutrons. If this phase transition happens inside the collapsing core, it actually softens the equation of state, making the matter more compressible rather than less. This accelerates the collapse. The very thing that might have provided additional resistance instead removes it. Other models propose the formation of hyperons, exotic heavy baryons containing strange quarks at these extreme densities. Hyperons are more massive than ordinary neutrons, and their formation absorbs energy from the system, again softening the equation of state and hastening the collapse. Whether the core passes through a quark-gluon plasma phase, a hyperon phase, or some other exotic state, the result is the same. The matter offers less resistance to compression than pure neutron matter would. The collapse accelerates rather than stalling. The proto-neutron star that briefly existed, that flickered into being for perhaps a few hundred milliseconds, is overwhelmed and crushed out of existence. The core crosses its own Schwarzschild radius, the critical size at which the escape velocity exceeds the speed of light. An event horizon forms. A black hole is born. Let me be clear about what this means physically, because the formation of a black hole is not just a more extreme version of forming a neutron star. It's a fundamentally different outcome. A neutron star has a surface. Material can hit that surface and bounce off. Energy can be radiated from that surface. A neutron star is an object that exists in space and interacts with its surroundings in incomprehensible ways. A black hole has no surface in the traditional sense. It has an event horizon, a mathematical boundary beyond which nothing can escape. Material that crosses the event horizon doesn't bounce. It doesn't reflect energy. It simply vanishes from the observable universe, adding its mass and angular momentum to the black hole. This distinction is critical for understanding why the hypernova explosion works differently from a supernova. In a supernova, the bounce off the neutron star surface is what initiates the explosion. Without that bounce, there's no shockwave. Without the shockwave, there's no explosion. So when a black hole forms instead of a neutron star, you might expect that the explosion simply doesn't happen. You might expect the entire star to just quietly collapse into the black hole, vanishing without a trace, producing nothing but a gravitational wave signature and a flood of neutrinos. And in fact, this does happen sometimes. Astronomers believe that some massive stars do collapse directly into black holes without producing any visible explosion at all. These are called failed supernovae, or sometimes unnovae. The star simply disappears. One day it's there, shining brightly. The next, it's gone, replaced by a black hole. There have been a few candidate observations of this phenomenon. A star in the galaxy NGC 6946, monitored by the Large Binocular Telescope, appeared to simply vanish between 2009 and 2015 without producing a bright supernova explosion. If confirmed, this would be direct evidence that some massive stars collapse into black holes without exploding. So, the question becomes, if forming a black hole removes the bounce mechanism that powers ordinary supernovae, how does a hypernova explode at all? What powers it? What makes it not just an explosion, but a more powerful explosion than a standard supernova? The answer lies in what happens to the material surrounding the newly formed black hole. Because the black hole doesn't form in isolation. It forms at the center of a collapsing star, and all the matter in that star, all the shells of silicon and oxygen and carbon and helium, all of it is still falling inward, falling toward the black hole. And this infalling matter doesn't just drop straight in. It can't, because of angular momentum. Angular momentum is one of the most fundamental conserved quantities in physics. It's the rotational equivalent of linear momentum. A spinning object tends to keep spinning, and a massive star, even if it appears to be rotating slowly, contains an enormous amount of angular momentum simply because of its size. When the core collapses, conservation of angular momentum causes the rotation rate to increase dramatically. This is the same principle that makes an ice skater spin faster when they pull their arms in. The core shrinks from the size of Earth to the size of a city, and its rotation rate increases by a factor of millions. The material falling toward the black hole has angular momentum too. It can't fall straight in along radial paths because its sideways motion prevents it. Instead, the infalling material spirals inward, forming a swirling disk of superheated matter around the black hole. This is called an accretion disk, and it's one of the most important structures in all of astrophysics. Accretion disks form around black holes in many different contexts, from stellar mass black holes in binary star systems to the supermassive black holes at the centers of galaxies. But the accretion disk that forms during a hypernova is special. It's temporary, lasting perhaps only 10 to 30 seconds. It's incredibly dense, fed by the ongoing collapse of the stellar envelope. And it's extraordinarily hot, with temperatures reaching billions of degrees. The physics of this accretion disk is what powers the hypernova. As matter spirals inward through the disk, friction between adjacent layers of material moving at different speeds generates enormous amounts of heat. The inner parts of the disk orbit the black hole faster than the outer parts, and the resulting shear forces convert gravitational potential energy into thermal energy with remarkable efficiency. How efficient? In principle, accretion onto a black hole can convert up to about 42% of the rest mass energy of the infalling material into other forms of energy. Compare this to nuclear fusion, which converts less than 1% of rest mass into energy. Accretion onto a black hole is roughly 50 times more efficient than nuclear fusion as an energy source. This is why black hole accretion is the most powerful, sustained energy generation mechanism known to physics. It's more efficient than fusion. It's more efficient than fission. It extracts energy from gravity itself, from the fundamental geometry of space-time. Now, not all of that theoretical maximum efficiency is realized in practice. Real accretion disks are messy, turbulent, and complicated. But even at a fraction of the theoretical maximum, the energy released by accreting even a small amount of material onto the newborn black hole is staggering. If just a few solar masses of material passes through the accretion disk during the 30 or so seconds that the hypernova engine operates, the energy released can exceed the entire energy output of a standard supernova by a factor of 10 or even 100. Let me put some numbers on this. A standard core collapse supernova releases about 10 to the power of 44 joules of kinetic energy, the energy that actually goes into blowing the star apart. A hypernova can release 10 to the power of 45 to 10 to the power of 46 joules of kinetic energy. That's 10 to 100 times more energy driving the explosion. And the total energy budget, including the energy carried away by neutrinos and the energy in the relativistic jets that we'll discuss soon, can be even higher. Some models suggest total energy outputs exceeding 10 to the power of 47 joules for the most extreme events. To put this in perspective, our Sun will release approximately 10 to the power of 44 joules over its entire 10 billion year lifetime. A hypernova releases 100 to 1,000 times that amount in a matter of seconds. It's almost difficult to write sentences about these numbers because the human brain has no intuitive framework for energy releases this large. There is nothing in everyday experience that scales to this. A nuclear bomb is about 10 to the power of 15 joules. A hypernova is about 10 to the power of 46 joules. That's a difference of 31 orders of magnitude. If you tried to match a hypernova's energy output by detonating nuclear bombs, you would need roughly 10 to the power of 31 of them. That's about 10 million times more nuclear bombs than there are stars in the entire observable universe. Every star you can see, every star in every galaxy across the cosmos, multiply that by 10 million, and you begin to approach the energy released by a single collapsing star in a few seconds. The accretion disk is also where the magnetic field becomes crucial. The material in the disk is ionized plasma, electrically charged particles moving at enormous speeds. Charged particles in motion generate magnetic fields. And in the extreme conditions of a hypernova accretion disk, these magnetic fields are amplified to extraordinary strengths through a process called the magnetorotational instability, or MMRI. This process, first described in detail by astrophysicist Stephen Balbus and John Hawley in 1991, shows how even a weak initial magnetic field can be amplified exponentially in a differentially rotating disk. The inner part of the disk orbits faster than the outer part. Magnetic field lines connecting material at different radii get stretched and amplified by this differential rotation. The field grows stronger and stronger, reaching values of 10 to the power of 15 Gauss or higher. For reference, Earth's magnetic field is about half a Gauss. The magnetic field in a hypernova accretion disk is roughly a quadrillion times stronger. These ultra-strong magnetic fields do something critical. They provide a mechanism for extracting rotational energy from the accretion disk and the black hole itself, channeling that energy into directed outflows along the rotational axis of the system. The magnetic field lines, anchored in the spinning disk, are wound up by the rotation into a tight helical configuration. This helical field acts like a nozzle, collimating the outflowing material into narrow jets that shoot outward from both poles of the black hole. But I'm getting ahead of myself. The jets are what we need to understand next. For now, What matters is understanding the role of the accretion disk in powering the hypernova. The disk converts gravitational energy into heat, radiation, and magnetic energy with extraordinary efficiency. It's the engine of the hypernova. Without the disk, the black hole would simply swallow everything quietly. With the disk, the death of the star becomes the most energetic explosion in the universe. There's another process happening simultaneously that contributes to the energy budget: neutrino annihilation. During the collapse and the early moments of accretion, neutrinos and antineutrinos are produced in enormous quantities. These neutrinos stream outward from the hot accretion disk. Above and below the disk, along the rotational axis, some of these neutrinos and antineutrinos collide with each other and annihilate, converting their mass energy into electron-positron pairs and gamma rays. This neutrino annihilation process deposits energy preferentially along the poles, where the density is lowest, and the neutrino fluxes from both sides of the disk overlap most effectively. This polar energy deposition helps clear a channel along the rotation axis, creating a funnel of low-density, high-energy material above and below the black hole. This funnel is where the jets will eventually form and propagate. The neutrino mechanism alone might not be sufficient to power the full hypernova explosion, but it contributes to creating the conditions that allow the magnetically driven jets to form and break free. It's worth pausing here to emphasize something about the timescale. Everything I've described, the core collapse, the formation of the black hole, the creation of the accretion disk, the amplification of magnetic fields, all of this happens in seconds. Not minutes, not hours, seconds. The core collapse itself takes less than 1 second. The black hole forms within milliseconds after the proto-neutron star fails. The accretion disk establishes itself within a second or two after that. The magnetic field amplification takes a few more seconds. The entire engine, from the beginning of a core collapse to a fully operational accretion-powered jet system, is up and running within roughly 10 seconds. 10 seconds. That's how long it takes for a star that has been shining for millions of years to transform from a stable, if extreme, stellar object into the most destructive engine in the cosmos. The star spent 4 or 5 million years fusing hydrogen, 500,000 years fusing helium, 1,000 years fusing carbon, a year fusing neon, months fusing oxygen, a day fusing silicon, and then 10 seconds rearranging the fundamental structure of space-time around its core, creating a black hole, forming an accretion disk, amplifying magnetic fields to quadrillion Gauss strengths, and unleashing an explosion that will outshine entire galaxies. The contrast between the timescales is itself remarkable. Millions of years of steady burning, then 1 day of silicon fusion, then 10 seconds of apocalypse. The star's death happens 1,000,000 times faster than its life. It's as if a person who lived for 80 years compressed their entire death into a single heartbeat. Now, I want to make something very clear, because this is the central point. The difference between a supernova and a hypernova is not just a matter of degree. It's not that a hypernova is simply a bigger bang. The underlying mechanism is fundamentally different. In a supernova, the explosion is powered by the bounce off a neutron star surface and by neutrino heating behind the stalled shockwave. In a hypernova, the explosion is powered by accretion onto a black hole and by the extraction of rotational and magnetic energy from the accretion disk. These are completely different physical processes. The supernova mechanism is essentially a mechanical bounce amplified by neutrino energy deposition. The hypernova mechanism is a gravitational engine that converts infalling mass into directed energy through the most efficient energy extraction process in nature. This distinction has real physical consequences. Supernova explosions are roughly spherical. The shock wave expands outward in all directions more or less uniformly. There's some asymmetry, some lumpiness, but the overall geometry is approximately spherical. Hypernova explosions are highly asymmetric. The energy is concentrated along the rotational axis of the collapsing core, channeled into narrow jets. The equatorial regions may explode too, driven by the enormous energy deposited by the disk winds and neutrinos. But the polar regions receive far more energy. The explosion is bipolar, not spherical. It looks completely different from a standard supernova. This asymmetry is also why hypernovae can be so much more energetic than supernova. In a supernova, the energy is spread over the entire solid angle of the explosion. In a hypernova, a significant fraction of the energy is concentrated into two narrow cones along the poles. If you happen to be looking down one of those cones, if the jet is pointed roughly in your direction, the apparent brightness is enormously amplified. The energy isn't really great in total than it would be if spread evenly. Well, actually, in a hypernova, the total energy is greater, but the concentration into jets makes the apparent energy output from a favored viewing angle even more extreme. Let me also address the question of what the black hole looks like at this stage. The newly formed black hole is small. A stellar mass black hole with a mass of, say, 3 solar masses has a Schwarzschild radius of about 9 kilometers. That's the radius of the event horizon, 9 kilometers. The entire black hole, the region from which nothing can escape, would fit comfortably inside a medium-sized city. And yet this tiny object, smaller than many asteroids, contains more mass than 2 or 3 suns. It is bending space-time so severely that light itself cannot climb out of its gravitational well. It is surrounded by a disk of matter hotter than the center of any star, threaded by magnetic fields stronger than anything else in the universe, and it is spinning at a significant fraction of the speed of light. The spin of the black hole is actually important. Not all black holes spin at the same rate. A black hole formed from the collapse of a rapidly rotating core will itself be rapidly rotating. This is described by the Kerr metric in general relativity, the mathematical solution that describes a rotating black hole. A maximally rotating black hole, one spinning as fast as physics allows, has properties significantly different from a non-rotating Schwarzschild black hole. The event horizon is smaller. There's a region outside the event horizon called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Objects in the ergosphere can actually extract rotational energy from the black hole through a process first described by Roger Penrose in 1969. This energy extraction from the spinning black hole may contribute to powering the jets. In the Blandford-Znajek mechanism, proposed by Roger Blandford and Roman Znajek in 1977, magnetic field lines threading the event horizon of a spinning black hole can tap into the black hole's rotational energy, extracting it and channeling it into the jets. This means the black hole itself becomes a power source. Its spin energy, which is enormous, can be converted into the kinetic energy of the jets. The black hole is not just a passive gravitational sink, it's an active participant in powering the explosion. The combination of accretion power from the disk and rotational energy from the spinning black hole creates an engine of almost incomprehensible power. And that engine operates for as long as the accretion disk is fed by infalling stellar material, which is typically about 10 to 30 seconds for the initial collapse, though some accretion may continue for minutes or even hours afterward at lower rates. During those 10 to 30 seconds, the engine produces jets, narrow beams of matter and energy that are accelerated to velocities approaching the speed of light. These jets are the signature of the hypernova mechanism. They're what makes the explosion so much more violent than anything a neutrino-driven bounce could produce. And they're what connects hypernovae to one of the most spectacular phenomena in all of astronomy, gamma-ray bursts. The jets have to bore through the collapsing star. They have to fight their way out from the center, punching through shells of silicon and oxygen and carbon and helium. If the star still has its hydrogen envelope, the jets may not make it out. They may stall inside the star, depositing their energy into the stellar interior and producing a spherical explosion rather than a jetted one. This is one reason why the Wolf-Rayet evolutionary phase matters so much. A star that has shed its outer hydrogen layers presents a smaller, more compact target. The jets have less material to punch through. They can break free of the stellar surface and escape into space, carrying their energy with them. When the jets do break free, when they punch through the surface of the dying star and erupt into the vacuum of space, something extraordinary happens. The jets are moving at 99% or more of the speed of light. They carry enormous energy concentrated into a narrow beam. And as they interact with the surrounding medium, as they slam into the gas and dust that surrounds the star, they produce radiation across the entire electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, and most spectacularly, gamma rays, the most energetic form of electromagnetic radiation in the universe. This is the connection between hypernovae and gamma ray bursts. When we detect a long-duration gamma ray burst, a sudden flash of gamma radiation lasting anywhere from a few seconds to a few minutes, we may be witnessing a hypernova in a distant galaxy. We're seeing the jets from a collapsing star, pointed by cosmic coincidence roughly in our direction. But we'll explore that connection in full detail shortly. For now, the key understanding is this. The core of an extraordinarily massive star collapses. It's too massive to form a stable neutron star. It collapses past neutron star density and forms a black hole. The surrounding stellar material, prevented by its angular momentum from falling directly into the black hole, forms an accretion disk. That accretion disk, combined with the spin of the black hole and amplified magnetic fields, creates the most powerful engine in the universe. An engine that operates for seconds but produces more energy than most stars produce in billions of years. An engine that doesn't explode the star through a mechanical bounce, but through the directed conversion of gravitational energy into relativistic jets of matter and radiation. This is the heart of a hypernova. Not a bigger bang, but a different kind of bang entirely. A different mechanism, a different engine, a different physics. The supernova bounces off a hard surface and spreads its energy in all directions. The hypernova falls into a bottomless pit and channels the energy of that fall into two narrow beams of almost inconceivable power. And those beams, those relativistic jets, are about to tear through the body of the dying star and announce its death to the universe in the most dramatic way possible. The black hole is born. The accretion disk is forming. Magnetic fields are being amplified to strengths that dwarf anything else in the known universe. And now, within seconds of the core's final collapse, the engine ignites. Two beams of matter and energy erupt from the poles of the accretion disk, punching upward and downward along the rotational axis of the dying star. These are the relativistic jets, and they are about to do something that no other astrophysical process can do. They are about to bore through the body of a collapsing star from the inside out, break free of its surface, and unleash a directed blast of energy so intense that it will be visible across the entire observable universe. Let me describe what these jets actually are, because the word jet doesn't really capture what's happening here. When most people hear the word jet, they think of a stream of water from a hose or the exhaust from a jet engine. Those are useful analogies for the shape, the narrow directed flow, but they completely fail to capture the physics. A relativistic jet from a hypernova is not a stream of ordinary matter moving at high speed. It's a magnetically confined torrent of plasma, electron-positron pairs, and radiation, accelerated to velocities exceeding 99% of the speed of light. At these speeds, the material in the jet experiences extreme relativistic effects, time dilation, length contraction, and an enormous increase in apparent energy due to relativistic beaming. The jet isn't just fast. It exists in a regime where the normal rules of Newtonian physics don't apply. It's a creature of Einstein's universe, shaped by the geometry of space-time itself. The jets are launched from the innermost regions of the accretion disk, very close to the event horizon of the black hole. The exact mechanism of jet launching is still an active area of research, but the leading models involve two complementary processes. The first is the Blandford-Znajek mechanism, which extracts rotational energy directly from the spinning black hole through magnetic field lines that thread the event horizon. The second is the magnetic tower or magnetocentrifugal mechanism, where magnetic field lines anchored in the accretion disk are wound up by the disk's rotation into a tight helical configuration that acts like a coiled spring, accelerating material outward along the rotational axis. In practice, both mechanisms likely operate simultaneously. The Blandford-Znajek process taps the black hole's spin energy, while the magnetocentrifugal process taps the rotational energy of the disk. Together, they create a dual-powered engine that converts gravitational and rotational energy into directed kinetic energy with extraordinary efficiency. The helical magnetic field structure is crucial. Imagine taking a straight magnetic field line and twisting it, winding it around and around like thread on a spool. As the accretion disk rotates, the magnetic field lines that pass through it are dragged along, twisted by the differential rotation into tighter and tighter coils. These coiled field lines create a pressure gradient along the rotational axis. The magnetic pressure is highest near the disk and decreases with distance along the axis. This pressure gradient accelerates material upward and downward, away from the disk, along the poles. The coiled field also confines the outflowing material, preventing it from spreading sideways. The result is a narrow, tightly focused beam of plasma and energy, collimated by the magnetic field into a cone with an opening angle of perhaps only a few degrees. The power carried by these jets is staggering. Theoretical models and simulations suggest that the jets can carry somewhere between 10 to the power of 44 and 10 to the power of 45 of 44 and 10 to the power of 46 joules per second. That's the power output, the rate of energy flow, sustained for the 10 to 30 seconds that the engine operates. Over the full duration, the total energy deposited into the jets can reach 10 to the power of 45 to 10 to the power of 47 joules. To put this in context, the entire luminosity of the Milky Way galaxy, all 100 billion to 400 billion stars combined, is about 10 to the power of 36 joules per second. The jets from a single hypernova can output roughly 10 billion times more power than our entire galaxy. For a few seconds, a single dying star outshines everything. Now, here's where the physics becomes truly remarkable. These jets don't emerge into empty space, they emerge into the interior of a collapsing star. The black hole is at the center. The accretion disk surrounds it. And beyond the disk, extending outward for millions of kilometers, are the remaining layers of the star, still falling inward under gravity. The jets have to fight their way through this material. They have to bore through the stellar envelope, like a drill through rock. And the dynamics of this interaction, the jet punching through the star, is one of the most complex and violent fluid dynamics problems in all of astrophysics. This is where the collapsar model comes in. The collapsar model, proposed in its modern form by astrophysicist Stan Woosley in 1993, describes exactly this scenario. The name collapsar is a contraction of collapsing star, and the model describes how a rapidly rotating massive star can collapse to form a black hole surrounded by an accretion disk, and how the resulting jets can produce both a hypernova explosion and a gamma ray burst. In Woosley's model, the sequence goes like this. A massive star, typically a Wolf-Rayet star that has lost its outer hydrogen envelope, reaches the end of its nuclear burning life. Its iron core collapses and forms a black hole. The rapidly rotating stellar material forms an accretion disk around the black hole. The disk powers relativistic jets along the rotational axis. These jets must then propagate through the remaining stellar envelope, a journey that takes several seconds before they can break free of the star's surface. The propagation of the jets through the star has been studied extensively using numerical simulations, computational models that solve the equations of relativistic hydrodynamics and magnetohydrodynamics on powerful supercomputers. These simulations reveal a complex interaction between the jet and the stellar material. The jet advances through the star not as a smooth, uniform beam, but as a turbulent, unstable flow. The leading edge of the jet, where it rams into the stellar material ahead of it, forms a structure called the jet head. The jet head is a region of intense interaction where the relativistic jet material collides with the much denser stellar material, creating a pair of shock waves. One shock, called the forward shock, propagates ahead of the jet into the stellar material, compressing and heating it. The other, called the reverse shock, propagates backward into the jet itself, decelerating and heating the jet material. The jet head advances through the star more slowly than the jet material itself is flowing. Think of it like water from a hose hitting a wall of sand. The water flows fast, but the hole it digs advances more slowly because the water has to push the sand out of the way. Similarly, the jet material moves at nearly the speed of light, but the jet head advances at perhaps 10 to 30% of the speed of light. The jet material piles up behind the jet head, forming a hot, turbulent region called the cocoon. The cocoon is important. As the jet bores through the star, The cocoon of shocked jet material and shocked stellar material expands sideways, pressing against the surrounding stellar envelope. This cocoon exerts pressure on the star from the inside, helping to unbind the stellar material and contributing to the overall explosion. Even regions of the star that aren't directly in the path of the jet can be affected by the cocoon's expansion. The cocoon helps make the explosion more spherical, even though the energy source is highly directional. The time it takes for the jet to traverse the star depends on the size of the stellar envelope. For a compact Wolf-Rayet star, which might have a radius of only about 1 to 5 solar radii, the jet can break through in roughly 5 to 15 seconds. For a star that has retained a more extended envelope, the breakout time can be much longer, perhaps 30 seconds or more. If the star is too large, if its envelope is too massive and too extended, the jet might never break through at all. It might stall inside the star, depositing all its energy into the stellar interior. In this case, you still get an explosion, but it's more spherical, and no gamma-ray burst is produced because the jets never escape the star. Some astronomers believe this might happen in some cases, producing energetic supernovae that are intermediate between ordinary supernovae and full hypernovae, bright and energetic, but without the extreme jet-driven characteristics. This is why the Wolf-Rayet phase is so critical for the hypernova mechanism. A star that has been stripped of its hydrogen envelope is more compact. Its remaining helium or carbon-oxygen envelope presents a smaller obstacle for the jets. The jets can punch through more quickly and break free before the engine runs out of fuel. A star that retains its full hydrogen envelope is much larger, potentially hundreds of times the radius of a Wolf-Rayet star. The jets would have to bore through vastly more material, and they might not make it out. The stripping of the outer layers, which happens through stellar winds during the star's life, is essentially what makes the hypernova visible as a gamma-ray burst. Without the stripping, the explosion still happens inside the star, but the jets are trapped. With the stripping, the jets break free and announce the star's death across the cosmos. When the jets finally do break through the surface of the star, the result is spectacular. The relativistic material, which has been confined inside the star and partially decelerated by its interaction with the stellar envelope, suddenly erupts into the vacuum of space. The jet material expands rapidly, accelerating back up to its full relativistic speed now that there's nothing to impede it. The breakout is accompanied by a burst of radiation, a flash of light and X-rays and gamma rays produced as the jet punches through the thin outer layers of the star and encounters the low-density material just above the stellar surface. After breakout, the jets continue to propagate outward into the circumstellar medium, the gas and dust surrounding the star. Much of this material was ejected by the star during its life through stellar winds. For a Wolf-Rayet star, the circumstellar environment can be quite complex, with multiple shells of material ejected during different phases of the star's evolution. The jets interact with this material, producing additional shocks and radiation. Meanwhile, back inside the star, the explosion is tearing the stellar envelope apart. The combination of the jet energy, the cocoon pressure, and the energy deposited by neutrinos and disk winds is blowing the star to pieces. The explosion is asymmetric, with more energy concentrated along the poles and less along the equator, but the entire star is being disrupted. Material is flung outward at speeds of tens of thousands of kilometers per second, creating an expanding shell of debris that will eventually form a supernova remnant. The total kinetic energy of this expanding debris is what defines the hypernova's explosive power. In a standard supernova, the kinetic energy of the ejector is about 10 to the power of 44 joules, often expressed as 1 pho, where pho stands for 10 to the power of 51 ergs, the unit commonly used in astrophysics. In a hypernova, the kinetic energy can reach 10 to 100 pho. That's 10 to 100 times more energy going into the actual disruption and ejection of stellar material. The ejector velocities are correspondingly higher. In a standard supernova, ejector speeds are typically around 5,000 to 10,000 kilometers per second. In a hypernova, the bulk ejector can move at 20,000 to 30,000 kilometers per second, with the jet material itself moving at more than 290,000 kilometers per second, over 99% of the speed of light. Let me talk more about what powers all this energy, because the efficiency of the accretion process deserves deeper explanation. When matter falls into a black hole from the accretion disk, it doesn't just fall straight in. It spirals inward, orbiting the black hole at increasing speeds as it gets closer. In the innermost regions of the disk, near the innermost stable circular orbit, the material is orbiting at a significant fraction of the speed of light. The gravitational potential energy released as the material spirals inward is converted into heat through viscous friction and magnetic stresses within the disk. The efficiency of this energy conversion depends on the spin of the black hole. For a non-spinning black hole, a Schwarzschild black hole, the innermost stable circular orbit is at 3 Schwarzschild radii, and the maximum radiative efficiency is about 5.7% of the rest mass energy of the accreted material. That might not sound like much, but remember that the rest mass energy of matter is enormous. E equals mc squared means that even a small amount of mass, when converted to energy, releases a staggering amount. 5.7% of the rest mass energy of one solar mass is about 10 to the power of 46 joules. That's already comparable to the total energy output of a supernova. For a rapidly spinning black hole, a Kerr black hole, the innermost stable circular orbit is closer to the event horizon, and the efficiency can be much higher. For a maximally spinning black hole, the efficiency can reach about 42%. 42% of rest mass converted to energy. This is astonishing. Nuclear fusion, the process that powers stars, converts less than 1% of rest mass to energy. Accretion onto a maximally spinning black hole is roughly 50 times more efficient. In the context of a hypernova, the black hole is likely spinning rapidly because it formed from the collapse of a rapidly rotating core. So the accretion efficiency is probably closer to the high end, perhaps 20 to 30% in realistic scenarios. If even a few solar masses of material passes through the accretion disk during the tens of seconds that the engine operates, the total energy released is enormous. One solar mass accreted at 20% efficiency yields about 3.6 times 10 to the power of 46 joules. That's more than enough to power a hypernova and a gamma-ray burst simultaneously. The disk also produces powerful winds, outflows of material that are launched from the surface of the disk at angles away from the rotational axis. These disk winds carry significant energy and momentum, and they contribute to the explosion in regions away from the poles. While the jets carry the most concentrated energy, the disk winds help ensure that the entire star is disrupted, not just the material along the polar axis. The combination of jets, disk winds, and neutrino heating creates a multi-component explosion that is far more complex and far more energetic than the simple, shock-driven explosion of an ordinary supernova. I want to emphasize something about the role of rotation because it's absolutely central to the entire hypernova mechanism. Without rapid rotation, you don't get a hypernova. You get either a normal supernova if the core is below the neutron star mass limit, or a failed supernova if the core is above the limit and collapses directly to a black hole without forming an energetic accretion disk. Rotation is what creates the accretion disk. Without angular momentum, the infalling material would fall directly into the black hole along radial paths. No disk would form, no friction would generate heat, no magnetic fields would be amplified, no jets would be launched. The black hole would simply swallow everything quietly. The star would vanish without producing any significant explosion. With rotation, the infalling material cannot fall directly in. It has to shed its angular momentum before it can cross the event horizon. This shedding of angular momentum is what creates the disk, powers the friction, amplifies the magnetic fields, and launches the jets. Angular momentum is not just a contributing factor to the hypernova mechanism, it's the essential ingredient. Without it, nothing works. This is why not every very massive star produces a hypernova. Some very massive stars may not rotate fast enough. Their cores might spin too slowly to form the kind of energetic accretion disk needed to power jets. These stars might collapse to black holes quietly, producing failed supernovae. Others might have intermediate rotation rates, producing explosions that are more energetic than typical supernovae, but less extreme than full hypernovae. The spectrum of outcomes depends sensitively on the rotation rate of the core at the moment of collapse. What determines whether a massive star retains enough angular momentum in its core to produce a hypernova? This is one of the major open questions in stellar astrophysics. Stars lose angular momentum throughout their lives through stellar winds and magnetic braking. The outer layers of the star can also transfer angular momentum to the core through various coupling mechanisms, or drain it away. The details of how angular momentum is transported within a massive star during its evolution are complex and not fully understood. One factor that seems to matter is metallicity, the abundance of elements heavier than hydrogen and helium in the star. Stars with lower metallicity tend to have weaker stellar winds, because the winds are driven partly by radiation pressure on heavy elements in the star's atmosphere. Weaker winds mean less mass loss, which means less angular momentum loss. Stars with low metallicity may therefore retain more of their rotational angular momentum, making them more likely to produce hypernovae and gamma-ray bursts. This prediction is consistent with observations. Gamma-ray bursts, which are linked to hypernovae, are more commonly observed in low metallicity galaxies. Small, metal-poor galaxies seem to produce proportionally more gamma-ray bursts than large, metal-rich galaxies like the Milky Way. Another factor might be binary interactions. If a massive star has a close companion, tidal interactions between the two stars can spin up the primary star, increasing its angular momentum. Mass transfer from the companion can also add angular momentum to the primary. Some models suggest that many hypernova progenitors might be in binary systems, with the companion star playing a crucial role in maintaining the rapid rotation needed for the hypernova mechanism. The importance of rotation also explains why hypernovae are rare. Most massive stars probably don't retain enough angular momentum in their cores. Most of them will die as ordinary supernovae, forming neutron stars. Some will collapse to black holes without exploding. Only a small fraction, those with the right combination of mass, rotation, and metallicity, will produce the full hypernova with relativistic jets and an associated gamma-ray burst. Estimates suggest that hypernovae might occur at a rate of roughly 1 for every 100 to 1,000 ordinary core collapse supernovae. They're rare events, but because they're so incredibly energetic, they can be detected at enormous distances. Let me paint a picture of what the explosion looks like as it develops, second by second, from the moment of core collapse. At time 0, the iron core exceeds the Chandrasekhar limit and begins to collapse. Within half a second, the core has compressed from the size of Earth to the size of a city, and the proto-neutron star has formed. Within a full second, the proto-neutron star has exceeded the Tolman-Oppenheimer-Volkoff limits and collapsed to form a black hole. The event horizon forms. The accretion disk begins to assemble from the rapidly rotating material falling inward. By 2 to 3 seconds, the accretion disk is fully established. Magnetic fields are being amplified by the magnetorotational instability. The helical field structure is beginning to form along the rotational axis. The first traces of outflowing material appear at the poles. By 5 seconds, the jets are fully launched. 2 beams of relativistic plasma are boring through the stellar envelope, advancing at perhaps 20% of the speed of light through the star's interior. The cocoon of shocked material is expanding around the jet channel, beginning to press on the stellar envelope. By 10 seconds, the jets have traversed a significant fraction of the stellar radius. If the star is a compact Wolf-Rayet, the jets may be approaching the surface. The cocoon has expanded substantially, beginning to unbind material from the star. Neutrinos from the accretion disk are depositing energy in the polar regions, further aiding the explosion. By 15 to 20 seconds, the jets break through the stellar surface. Relativistic material erupts into space. A flash of radiation accompanies the breakout. From this moment, if the jets happen to be pointed toward a distant observer, that observer will soon detect a gamma-ray burst. By 30 seconds, the main engine is winding down. The accretion rate onto the black hole is decreasing as the supply of stellar material is exhausted. The jets are weakening but still active. The stellar envelope is being blown apart by the combined effects of the jets, the cocoon, and the disk winds. The star is dying in the most violent way possible. By 1 minute, the explosion is well underway. The stellar debris is expanding outward at thousands of kilometers per second. The jet material is racing ahead at nearly the speed of light, already millions of kilometers from the explosion site. The black hole sits at the center, surrounded by the remnants of the accretion disk, still slowly consuming whatever material remains nearby. By 1 hour, the expanding debris has reached hundreds of millions of kilometers from the explosion site. The jet has propagated billions of kilometers into space, interacting with the circumstellar medium and producing radiation across the electromagnetic spectrum. The hypernova is now visible as a brightening point of light in whatever galaxy it occurred in, growing brighter as the expanding fireball radiates the thermal energy deposited during the explosion. By 1 day, the hypernova is already visibly brightening in its host galaxy, growing more luminous as the expanding fireball radiates the thermal energy deposited during the explosion. The radioactive decay of nickel-56 is now heating the ejector from within, driving the light curve steadily upward. By 2 weeks, the hypernova has reached its peak optical brightness. For a brief period, it shines with a luminosity of several billion suns or more. In its host galaxy, particularly if the host is a small dwarf galaxy, as is common for these events, it can outshine every other star combined. From Earth, if the hypernova occurred in a galaxy billions of light years away, it would be visible as a transient point of light detectable by modern survey telescopes. By 4 to 6 weeks, the optical brightness is fading. The expanding debris is becoming optically thin, allowing radiation from the interior to escape more easily. The light curve at this stage is powered by the ongoing radioactive decay chain, as cobalt-56 continues to decay to stable iron-56, releasing gamma rays and positrons that heat the thinning ejector and sustain its glow as it slowly dims over the following months. And this is where the story shifts from the mechanics of the explosion to its consequences. Because a hypernova doesn't just destroy a star, it transforms the composition of the debris, forging heavy elements in conditions so extreme that they can't be replicated anywhere else in the universe. It sends relativistic jets across billions of light years, producing gamma-ray bursts that are the most luminous electromagnetic events ever observed. It leaves behind a black hole that will persist for an almost incomprehensible length of time, and it seeds the surrounding space with the materials that will eventually be incorporated into new stars, new planets, and possibly new life. The death of this monster star is not just an ending, it's also a beginning. And what it begins, what it creates in its final violent seconds, connects directly to the atoms in your body and the ground beneath your feet. The jets have broken free. The star is being torn apart from the inside out. And now, racing outward at 99.9% of the speed of light, two narrow beams of energy and matter are about to announce this star's death to the universe in the most dramatic way physics allows. Because when those jets interact with the surrounding environment, when their energy is converted into radiation, they produce something that astronomers have been detecting and puzzling over for decades: gamma ray bursts, the most energetic electromagnetic events in the observable universe, and understanding the connection between hypernovae and gamma ray bursts is one of the great detective stories in modern astrophysics. Gamma ray bursts were discovered by accident. In the late 1960s, the United States launched a series of military satellites called the Vela satellites. Their purpose had nothing to do with astronomy. They were designed to detect nuclear weapons tests in violation of the Partial Nuclear Test Ban Treaty of 1963. The satellites carried gamma-ray detectors because nuclear detonations produced distinctive bursts of gamma radiation. The idea was simple. If the Soviet Union secretly tested a nuclear weapon in space or on the far side of the moon, the Vela satellites would detect the gamma-ray flash. The satellites worked. They detected gamma-ray bursts. But the bursts weren't coming from Earth or from Soviet nuclear tests. They were coming from deep space, from random directions in the sky. The first burst was detected on July 2nd, 1967 by the Vela 3 and Vela 4 satellites. The data was classified for several years. It wasn't until 1973 that Ray Klebus-Adel, Ian Strong, and Roger Olson at Los Alamos National Laboratory published the discovery, reporting 16 gamma-ray bursts detected between 1969 and 1972. The bursts came from all over the sky with no preferred direction. They lasted anywhere from fractions of a second to several minutes, and nobody had any idea what was causing them. For the next 2 decades, gamma-ray bursts remained one of the deepest mysteries in astronomy. More than 100 theoretical models were proposed to explain them. Some suggested they came from nearby neutron stars in our galaxy. Others proposed they came from the edges of the observable universe. Without knowing the distances to the bursts, it was impossible to determine how much energy they involved, and therefore impossible to narrow down the physical mechanism. The breakthrough came in the 1990s with 2 key developments. First, the Compton Gamma Ray Observatory, launched in 1991, carried an instrument called BATS-E, the Burst and Transient Source Experiment. BATS-E detected thousands of gamma-ray bursts and showed that they were distributed uniformly across the sky, with no concentration toward the plane of the Milky Way or toward any nearby galaxy clusters. This strongly suggested that the bursts were cosmological, coming from enormous distances, not from within our galaxy. Second, in 1997, the Italian-Dutch satellite Bepi-SAX detected a gamma-ray burst designated GRB 970228 and, for the first time, was able to determine its position precisely enough for optical telescopes to identify an afterglow, a fading point of light at the burst location. Spectroscopic observations of this afterglow revealed a redshift of 0.695, corresponding to a distance of roughly 6 billion light-years. This confirmed that gamma-ray bursts were indeed cosmological, occurring in distant galaxies, and at those distances, the energy required to produce the observed gamma-ray flux was absolutely staggering. If the energy were emitted uniformly in all directions, a single burst would release more energy than the Sun would produce in its entire 10 billion year lifetime, compressed into a few seconds. Astronomers quickly realized that gamma-ray bursts fell into 2 categories: short-duration bursts, lasting less than about 2 seconds, and long-duration bursts, lasting from a few seconds to several minutes. The 2 categories had different properties. Short bursts had harder spectra, meaning their gamma rays were on average more energetic. Long bursts had softer spectra and were often followed by longer-lasting afterglows. It became clear that these 2 categories were produced by different physical mechanisms. Short-duration gamma-ray bursts are now understood to be produced by the merger of 2 compact objects, typically 2 neutron stars or a neutron star and a black hole. This was spectacularly confirmed in 2017 when the LIGO and Virgo gravitational wave detectors observed a neutron star merger designated GW170817, and the Fermi Gamma Ray Space Telescope simultaneously detected a short gamma-ray burst from the same location. This was one of the most important observations in the history of astronomy, confirming the connection between neutron star mergers and short gamma-ray bursts. Long-duration gamma-ray bursts are the ones connected to hypernovae, and the evidence for this connection built up gradually over years of careful observation. The key piece of evidence came from a burst detected on March 29th, 2003. GRB030329 was a bright, long-duration gamma-ray burst at a redshift of 0.169, corresponding to a distance of about 2 billion light-years. That's relatively close by gamma-ray burst standards, close enough that astronomers could study the afterglow in detail as it faded over the following weeks. As the afterglow faded, something remarkable happened. A supernova appeared at the same location. The supernova, designated SN 2003-DH, brightened as the afterglow dimmed, eventually dominating the light from the explosion. Spectroscopic observations revealed that SN 2003-DH was a broad-lined Type 1c supernova, meaning it showed no hydrogen or helium in its spectrum, consistent with a stripped envelope star like a Wolf-Rayet. And it had extremely broad spectral lines, indicating ejector velocities of roughly 30,000 kilometers per second, much faster than ordinary supernovae. The kinetic energy of the explosion was estimated at roughly 30 to 50 times that of a standard supernova, but SN 2003-DH was not the first clue. 5 years earlier, astronomers had already noticed something unusual. In 1998, a gamma-ray burst designated GRB 980425 was detected, and within days, a remarkably bright supernova appeared at the same location. That supernova, SN 1998 BW, was peculiar. It was classified as a Type 1c supernova, meaning it showed no hydrogen and no helium in its spectrum, consistent with a stripped envelope progenitor. But its spectral lines were extraordinarily broad, far broader than those of any previously observed Type IC supernova. Those broad lines indicated ejector velocities of roughly 30,000 kilometers per second, several times higher than typical supernova ejector, and its peak luminosity was enormous, roughly 10 times brighter at maximum light than a standard Type X supernova. The total kinetic energy inferred from the observations was staggering, somewhere around 30 times the canonical supernova energy. SN 1998 BW was the first event that astronomers began calling a hypernova, and the term has stuck ever since. Other notable hypernova candidates have been identified over the years. SN 2002 AP, observed in the galaxy NGC 627, showed the same hallmarks: extremely broad spectral lines, high ejector velocities, and a kinetic energy far exceeding that of normal supernovae. SN 2010 BH in the dwarf galaxy U GC 2022 was another strong candidate, exhibiting the characteristic broad-lined Type 1c spectrum and extreme luminosity. Each new observation added weight to the emerging picture. These were not ordinary stellar deaths. They were something fundamentally more violent, more energetic, and physically distinct from the supernovae astronomers had been studying for decades. GRB 030329 and SN 2003-DH became the definitive case. A long-duration gamma-ray burst and a hypernova, occurring at the same place at the same time from the same star. SN 1998. BW had raised the possibility years earlier, and the growing list of hypernova candidates had made the pattern harder to dismiss. But this was the event that removed all reasonable doubt. The association between long gamma-ray bursts and hypernovae was confirmed. Since then, several more associations have been confirmed, firmly establishing the paradigm: long-duration gamma-ray bursts are produced by hypernovae. Specifically, they're produced by the relativistic jets that punch through the surface of a collapsing Wolf-Rayet star. The gamma-ray burst is what you see when one of those jets happens to be pointed roughly in your direction. This raises an important point about geometry. The jets from a hypernova are narrow, typically collimated into cones with opening half angles of about 2 to 10 degrees. This means the gamma rays are beamed into a small fraction of the sky. If the jets aren't pointed at you, you don't see the gamma ray burst. You might still see the supernova component, the expanding debris from the explosion, but you wouldn't detect the gamma rays. This beaming effect has a profound implication. For every gamma ray burst we detect, there are many more hypernovae occurring whose jets are pointed away from us. Depending on the jet opening angle, the ratio could be anywhere from about 100 to 500 to 1. For every gamma ray burst we observe, there might be hundreds of hypernovae happening that we never detect as gamma ray bursts. We might detect some of them as unusually energetic supernovae, but most would appear as ordinary bright supernovae without the dramatic gamma ray signature. This means hypernovae are more common than gamma ray bursts alone would suggest. The beaming also explains why gamma ray bursts appear so extraordinarily energetic. When we calculate the energy of a gamma ray burst, we initially assume the energy is radiated uniformly in all directions, what astronomers call isotropic emission. Under this assumption, some bursts appear to release 10 to the power of 47 joules or more, an almost inconceivable amount. But because the energy is actually concentrated into a narrow beam, the true total energy is lower by a factor related to the beaming angle. If the jet has an opening angle of 5 degrees, the beamed energy is only about 1/500th of the apparent isotropic energy. This brings the true energy down to about 10 to the power of 44 to 10 to the power of 45 joules, which is still enormous, but more physically reasonable. Let me describe what a gamma ray burst looks like from the perspective of an observer. Imagine you're on Earth, and a hypernova occurs in a galaxy 2 billion light years away. The jets happen to be pointed in our general direction. Here's what you would observe. First, there's nothing, no warning. The star is too distant to see. Then, a satellite in orbit detects a sudden flash of gamma radiation. The flash lasts perhaps 20 seconds. During those 20 seconds, the gamma ray detector registers an intense pulse of high-energy photons, with energies ranging from tens of thousands to millions of electron volts. The burst has a complex temporal structure, with multiple peaks and dips, reflecting the turbulent, variable nature of the jet as it breaks through the stellar surface and interacts with the surrounding medium. Within seconds of the burst detection, automated systems aboard the satellite determine the approximate position on the sky and transmit coordinates to ground-based telescopes around the world. Within minutes, optical telescopes slew to the position and begin imaging. They detect a faint point of light that wasn't there before. This is the afterglow, produced as the jet decelerates by plowing into the surrounding medium. The afterglow fades over the following hours and days, transitioning from X-ray to optical to radio wavelengths as the shock wave slows and the emission shifts to lower energies. Over the following weeks, as the afterglow fades, a second component becomes visible, the supernova. The expanding debris from the destroyed star breathes, peaks after a week or two, and then slowly fades. By analyzing the spectrum of this supernova component, astronomers can determine the composition of the ejector, the velocity of the expanding material, and the total energy of the explosion. This is how the hypernova gamma ray burst connection has been studied. Each new burst supernova association adds to our understanding, and each one confirms the same basic picture. A massive, rapidly rotating star collapses. A black hole forms, An accretion disk powers relativistic jets. The jets break through the star and produce a gamma ray burst. The rest of the star is blown apart in a hypernova explosion. Now, let's turn to what a hypernova creates, because destruction on this scale is also creation on a cosmic scale. The extreme conditions inside a hypernova, the enormous temperatures, the intense neutron fluxes, the violent shock waves forge elements that cannot be produced in any other environment. And some of those elements are essential to the existence of planets like Earth and life like us. During normal stellar evolution, fusion in the cores of massive stars produces elements up to iron on the periodic table. Iron is the endpoint of exothermic fusion. You cannot get energy out of fusing iron into heavier elements. But the universe contains elements heavier than iron. Gold, platinum, uranium, thorium, all the way up to element 92 and beyond in artificial settings. Where do these elements come from? They come from environments where neutrons are available in enormous abundance and can be captured by atomic nuclei faster than those nuclei can decay. This process is called rapid neutron capture, or the R process. The R stands for rapid, and it distinguishes this process from the slow neutron capture process, or AS process, which occurs in the interiors of certain evolved stars called asymptotic giant branch stars. In the S process, neutron captures happen slowly enough that unstable nuclei have time to undergo beta decay between captures. This produces a specific set of heavy elements along the valley of stability on the nuclear chart. The R process is completely different. Neutron captures happen so rapidly that nuclei accumulate neutrons far faster than they can decay. The nuclei are driven far to the neutron-rich side of the nuclear chart, into exotic territory where the nuclei are extremely unstable. Only after the neutron flux subsides do these neutron-rich nuclei undergo a cascade of beta decays, converting neutrons to protons and climbing back toward the valley of stability, producing the characteristic R process elements. The R process requires conditions of extreme neutron density, temperatures in the billions of degrees, and very short timescales on the order of seconds. These conditions exist in at least two known astrophysical environments: neutron star mergers and hypernovae. The 2017 neutron star merger, GW170817, provided the first direct evidence of R process nucleosynthesis in a merger event. The electromagnetic counterpart of that merger, called a kilonova, showed spectral signatures consistent with the production of heavy R process elements, including lanthanides. But neutron star mergers are not the only sight. Hypernovae also produce the conditions necessary for the R process, particularly in the neutrino-driven winds from the accretion disk surrounding the black hole. These winds are heated to enormous temperatures by neutrinos streaming from the disk. The material in the winds is rich in neutrons because the intense neutrino flux drives nuclear reactions that favor a high neutron-to-proton ratio. As this neutron-rich material is ejected from the system and expands, it cools rapidly, and the R process kicks in. Neutrons are captured by seed nuclei at an enormous rate, building up heavy elements in a matter of seconds. The relative contribution of hypernovae versus neutron star mergers to the total inventory of R process elements in the universe is still debated. Some models suggest that neutron star mergers dominate the production of the heaviest R process elements, those heavier than silver and gold. Others suggest that hypernovae contribute significantly, particularly to the lighter R process elements, and possibly to some of the heavier ones as well? The answer likely depends on the detailed physics of both environments, physics that researchers are still working to understand. What is clear is that hypernovae contribute substantially to the chemical enrichment of the universe. The debris from a hypernova expanding outward at thousands of kilometers per second carries with it a rich mixture of elements forged during the star's life and during its violent death. Silicon, sulfur, calcium, titanium, iron, nickel, and many other elements are scattered into the surrounding interstellar medium. Over millions of years, this debris mixes with the ambient gas and dust in the galaxy. Eventually, some of this enriched material is incorporated into new molecular clouds, which collapse to form new stars and new planetary systems. This is how the elements in your body were made. The calcium in your bones was forged in the oxygen-burning shell of a massive star. The iron in your blood was produced during silicon burning in the final day of a star's life. Some of the heavier elements in your body, the iodine in your thyroid, the trace amounts of gold and platinum that exist in Earth's crust, may have been produced in the R process during a hypernova or a neutron star merger that occurred billions of years ago, long before our sun was born. The hypernova also produces enormous quantities of radioactive nickel-56, far more than an ordinary supernova. While a standard core collapse supernova might produce roughly 0.05 to 0.1 solar masses of nickel-56, a hypernova can forge half a solar mass or more. This overproduction has consequences beyond just the brightness of the explosion. When the nickel-56 decays through its chain to stable iron-56, that iron is ejected into the interstellar medium along with all the other debris. Hypernovae are therefore disproportionate contributors to the iron content of the universe. A single hypernova can inject as much iron into its surroundings as dozens of ordinary supernovae. Over cosmic time, these rare but prolific events have helped build up the iron abundance in galaxies, contributing to the iron that eventually ends up in the cores of rocky planets and in the bloodstreams of living organisms. This brings up an important observational distinction. If you were an astronomer studying a hypernova through a telescope, without the benefit of detecting a gamma-ray burst, how would you know it wasn't just an ordinary supernova? The answer lies in the spectra and the energetics. Hypernovae are classified as broad-lined Type 1c supernovae, sometimes abbreviated as Type 1c-BL. The Type IC designation means no hydrogen and no helium are visible in the spectrum, indicating the progenitor star had been stripped of its outer layers. The broad line designation refers to the extreme width of the spectral absorption features, which are Doppler broadened by the high velocities of the expanding ejecta. In a hypernova, the ejecta velocities are so much higher than in ordinary supernovae that the absorption features in the spectrum are Doppler smeared into wide troughs rather than the narrow dips seen in standard events. The spectral lines are so broad that they blend, creating a smoother, more featureless spectrum than ordinary supernovae. The light curve also rises faster and peaks at a higher luminosity, often 10 to 100 times brighter than a standard core collapse supernova, reflecting the much greater energy deposited into the ejecta and the larger mass of radioactive nickel-56 produced. Now, let's talk about the reach of a hypernova. How far does the destruction extend? What would happen if a hypernova occurred near our solar system? The radiation from a hypernova is intense. The gamma-ray burst, if one of the jets is pointed at you, delivers an enormous flux of high-energy photons. At a distance of a few thousand light years, this radiation could have serious consequences for a planet like Earth. The gamma rays would interact with the atmosphere, destroying ozone molecules in the stratosphere. The ozone layer protects life on Earth from harmful ultraviolet radiation from the sun. With the ozone layer depleted, ultraviolet radiation would reach the surface at much higher levels, causing widespread DNA damage in organisms, disrupting ecosystems, and potentially triggering a mass extinction. Some researchers have proposed that a gamma-ray burst may have been responsible for the Ordovician-Silurian extinction event about 445 million years ago, one of the 5 great mass extinctions in Earth's history. During this event, roughly 85% of marine species went extinct. The evidence for a gamma-ray burst cause is circumstantial, based on the pattern of extinctions, which preferentially affected organisms in shallow water that would have been more exposed to increased ultraviolet radiation. The hypothesis remains speculative, but it illustrates the potential danger that these events pose. Fortunately, hypernovae and their associated gamma-ray bursts are rare. They occur perhaps once every few 100,000 years in a galaxy like the Milky Way. And because the jets are narrow, the chance of one being pointed directly at Earth is small. The probability of a gamma-ray burst occurring close enough and aimed precisely enough to cause significant harm to Earth is estimated at roughly once every few 100 million years. It's a real risk on geological timescales, but not something you need to worry about on human timescales. Even without the gamma-ray burst, a hypernova occurring within a few dozen light years of Earth would be dangerous. The blast wave from the expanding debris would take thousands of years to reach us, but the radiation, the X-rays, and ultraviolet light from the explosion would arrive at the speed of light. The cosmic rays, high-energy particles accelerated by the expanding shockwave, would arrive over a period of years to centuries, bathing the solar system in elevated radiation levels that could affect the ozone layer and increase mutation rates in living organisms. On longer timescales, the debris from a hypernova creates a supernova remnant, an expanding shell of hot gas and magnetic fields that could persist for tens of thousands of years. But hypernova remnants differ from ordinary supernova remnants in important ways. The higher kinetic energy of the explosion means the blast wave expands faster and sweeps up interstellar material more aggressively. The result is a larger, more energetic remnant that can span hundreds of light years across over tens of thousands of years. The shock front at the leading edge of the remnant compresses and heats the surrounding interstellar gas to temperatures of millions of degrees, causing it to glow in X-rays. The interior of the remnant is enriched with the heavy elements forged during the explosion, creating bubbles of chemically enriched gas that slowly mix with the surrounding interstellar medium over hundreds of thousands to millions of years. These enriched regions become the raw material for future generations of stars and planets. If the hypernova produced relativistic jets, the remnant may also show an elongated or bipolar morphology, stretched along the axis of the original jets. This asymmetry can persist for thousands of years, leaving a fingerprint of the jets long after they've dissipated. Observers studying ancient remnants can sometimes reconstruct the geometry of the original explosion by mapping the shape and chemical distribution of the debris, reading the fossil record of a star that died violently thousands of years ago. But let's step back from the dangers and think about what hypernovae mean for the universe as a whole. Because these events, as violent as they are, play a crucial role in cosmic evolution. Hypernovae are one of the primary mechanisms by which the universe recycles material. Stars form from gas, fuse light elements into heavy ones during their lives, and then return that processed material to the interstellar medium when they die. Ordinary supernovae contribute to this recycling, but hypernovae contribute disproportionately because they involve the most massive stars, which produce the most heavy elements, and because the explosions are so energetic that they distribute that material over enormous volumes of space. The energy deposited by hypernovae into the interstellar medium also drives turbulence and triggers new star formation. The expanding shock waves from hypernovae compress nearby gas clouds, pushing them past the threshold of gravitational collapse and initiating the formation of new stars. Some of those new stars will themselves be massive enough to eventually die as supernovae or hypernovae, continuing the cycle. The death of one generation of stars seeds the birth of the next. What remains after the explosion fades is a black hole, a stellar mass black hole, typically between about 3 and perhaps 30 solar masses, depending on how much material fell into the black hole during the explosion and how much was ejected. This black hole will persist for an almost unimaginable length of time. According to Stephen Hawking's theory of black hole evaporation, black holes slowly radiate energy through a quantum mechanical process called Hawking radiation, but the rate of evaporation is incredibly slow. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate. That's a number so large that it dwarfs the current age of the universe by a factor of 10 to the power of 57. The black hole born in a hypernova will outlast every star, every planet, every galaxy in the observable universe. Long after the last star has burned out, long after the last planet has frozen and crumbled, the black holes will still be there, slowly evaporating in the cold, dark emptiness of a dying universe. There's something poetic in that. The most violent event in the universe creates one of the most enduring objects. The explosion lasts seconds. The black hole lasts longer than the universe itself will remain recognizable. Destruction and permanence bound together in the same event. As I bring this journey to a close, I want you to think about what we've covered tonight. We started with a monster star, a blue giant with 40 or more times the mass of our sun, burning through its nuclear fuel at a furious rate, building an onion-layered interior of progressively heavier elements. We watched that star shed its outer layers through fierce stellar winds, stripping itself down to a naked wolf-ray at core, unknowingly preparing itself for the most violent death possible. We followed the iron core as it grew beyond the Chandrasekhar limit and collapsed in less than a second, falling inward at a quarter of the speed of light, crushing itself, past neutron star density into a black hole. We saw the accretion disk form from the rapidly rotating infalling material, watched as magnetic fields were amplified to quadrillion Gauss strengths, and witnessed the birth of relativistic jets, twin beams of matter and energy that bored through the dying star from the inside out. We saw those jets break free of the stellar surface and produce a gamma-ray burst visible across billions of light years, and we traced the aftermath, the heavy elements forged in the explosion, the R process creating gold and platinum and uranium, the expanding debris seeding the interstellar medium with the raw materials for new stars and new worlds. Every step of this process pushes physics to its absolute limits. The densities exceed anything found in ordinary matter. The temperatures surpass the interiors of the most extreme stars. The magnetic fields are stronger than anywhere else in the universe. The velocities approach the fundamental speed limit imposed by the structure of space-time. And the energies released in a few seconds exceed the total output of most stars over their entire lifetimes. A hypernova is the universe operating at maximum intensity. It is nature's most extreme statement about what happens when gravity wins. When the most massive stars reach the end of their fuel and nothing in physics can prevent the final collapse. And yet, out of this ultimate destruction comes creation. The elements forged in hypernovae are scattered across space and incorporated into the next generation of stars and planets. The gold in a ring on someone's finger, the iodine in a child's thyroid gland, the uranium decaying deep in Earth's mantle and helping to keep our planet's core molten and its magnetic field alive. Some of these atoms may have been born in the heart of a hypernova billions of years ago. A star died in the most violent way possible, and from its ashes eventually arose everything you see around you, including you, the iron in your blood, the oxygen you're breathing right now, the carbon that forms the backbone of every molecule in your body. All of it was forged inside stars. Some of it in ordinary stars that died quiet deaths. Some of it in supernovae. And some of it, perhaps some of the rarest and most precious atoms in your body, in the cataclysmic fury of a hypernova. You are, in the most literal and scientifically precise sense, made from the debris of exploding stars. And some of those explosions were not ordinary explosions. Some of them were the most violent events the universe has ever produced. You carry within you the legacy of cosmic catastrophes that occurred before our sun was born, before our galaxy had settled into its current shape, in an era when the universe was young and violent, and still forging the elements that would one day make life possible. That's what a hypernova really is. Not just the death of a star, not just an explosion. It's a forge, a crucible in which the universe creates the complex elements necessary for rocky planets, liquid water, organic chemistry, and ultimately life. The most destructive force in the cosmos is also, in its own way, one of the most creative. Without these catastrophic deaths, the universe would be a simpler, emptier place. A cosmos of hydrogen and helium, and not much else. No planets, no oceans, no iron, no gold, no carbon, no life. So the next time you look up at the night sky and see a star twinkling peacefully in the darkness, remember what you've learned tonight. Some of those stars, the biggest and brightest ones, are destined to die in hypernovae. They will collapse, form black holes, launch relativistic jets, and explode with an energy that defies comprehension. And from their deaths, new worlds will eventually be born. The universe destroys to create. It annihilates to build. And the most violent events in all of nature are also the events that made your existence possible. That is what actually happens during a hypernova. And now you know. Thank you for joining me on this journey into one of the most extreme phenomena in the universe. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. Sleep well tonight, knowing that the atoms in your body were forged in the hearts and deaths of ancient stars. Some of them in explosions so violent that they briefly outshone everything else in the universe. You are stardust. And some of that stardust was born in fire beyond imagination. Good night.